In this video, we're going to focus on solving thermodynamic problems, particularly problems associated with internal energy, heat, work, isothermal, isochoric, adiabatic processes, and even isobaric processes. But first, let's go over the equations that we need to know. Let's organize it into a table. So on the left side, the first column, we're going to talk about the different types of processes that you need to know. And then here we're going to have the equations for work, Q, which represents the heat flow into or out of the system, and also delta U, the change in internal energy. So the first process that we're going to talk about is the isochoric process. Now, for an isochoric process, what you need to know is that the change in volume is equal to 0. The volume is constant. And because the volume is constant, the work done for an isochoric process will always be equal to 0. Now, the change in internal energy is equal to Q minus W. So therefore, since W is 0, the change in internal energy will simply be equal to Q. To calculate Q, you can use this equation. It's equal to N times CV times delta T. Now, if you don't know what these variables mean, don't worry, just sit back, relax, take notes. Throughout the video, I'm going to explain how to use these equations and also when to use them. I'm going to give you plenty of practice problems for you to work on. But you need to know that N represents the number of moles. CV is basically the molar heat capacity when the volume is constant of an ideal gas. And delta T is the change in temperature. Delta T can be in Kelvin or Celsius. Anytime you see just T in the equation without the triangle, the temperature has to be in Kelvin. If you see the triangle associated with it, it can be in Celsius or Kelvin. The change in temperature in Celsius and Kelvin is the same. But when you multiply or divide by T, it has to be in Kelvin. Now, the next thing that we need to talk about is the isobaric process. In an isobaric process, the change in pressure is equal to 0. The pressure is constant. Under constant pressure conditions, you can calculate the work using this equation. It's equal to the pressure times the change in volume. By the way, you can also calculate the work using this equation. NR times delta T. We'll talk more about that throughout this video. Now, what about Q for an isobaric process? What equation will be useful to us? So, like the equation above, Q is going to be equal to NC delta T. But instead of CV, it's going to be CP because we're dealing with constant pressure. CP is the molar heat capacity of a gas measured at constant pressure, and then times the change in temperature. Now, delta U, you can always use this equation. It's the heat minus the amount of work. Now, another equation that you can use to calculate delta U for any process is this equation. It's NCV delta T. Keep in mind, delta U is equal to Q for an isochoric process, but delta U is always equal to NCV times delta T. Now, the next thing that we need to talk about is an isothermal process. Under this process, the temperature is constant. So delta T is equal to 0. Now, because the change in temperature is equal to 0, notice that delta U will be equal to 0. So under isothermal conditions, the change in internal energy is always equal to 0. If that's the case, then Q minus W is equal to 0, which means that Q is equal to W. So how do we calculate the work or the heat exchange in an isothermal process? Let's see if I can fit this equation in here. So one way to do it is to use this equation. Work is equal to N RT natural log the final volume divided by the initial volume. Another equation that you can use in terms of pressure, keep in mind if you want to find Q, it equals this as well, but you can also use this equation. It's equal to nRT times the natural log the initial pressure divided by the final pressure. Pressure and volume are inversely related. By the way, make sure you know the gas laws, because with these types of problems, you're going to be dealing with gases. For example, in an isochoric process, because the volume is constant, if the temperature increases, the pressure will increase. Therefore, you can use this equation. P1 divided by T1 is equal to P2 divided by T2 for an isochoric process. Now what about an isobaric process where the pressure is constant? Whenever you increase the temperature at constant pressure, the volume has to increase. If you've taken chemistry and you've studied the gas laws, this is known as Charles' law. Whenever you heat a gas, the gas will expand. Now the equation that you need for this type of situation is V1 divided by T1 is equal to V2 divided by T2. Now there's a lot more equations that we need. Under isothermal conditions, if you increase the pressure, the volume will decrease. And likewise, if you increase the volume, the pressure will decrease. Volume and pressure are inversely related. This is known as Boyle's law. So the equation that is associated with Boyle's law is P1V1 is equal to P2V2. Now the last process that we need to go over is the adiabatic process. Under this process, Q is equal to 0. So what this means is that no heat flows into or out of the system. Now this can occur if, let's say, the process occurs quickly or if it's well insulated. Because heat takes time to flow from one place to another, a process that happens quickly will allow a very small amount of heat to travel through. So basically you could say Q is almost 0. I should have put that in this column. Now, because Q is equal to 0, that means that the change in internal energy is equal to negative W. So let's write that over here. So delta U is equal to negative W. And delta U is always equal to NCV delta T, which means that the work is equal to negative N, the number of moles, times CV, the molar heat capacity at constant volume, times the change in temperature. Now there are some other equations associated with this process. And I'm going to add that throughout this video. But something that you need to know is that CV for a monoatomic gas is equal to 3/2 times R. And that's true for any of these processes. A monoatomic gas is simply a gas that contains one atom. For a diatomic gas, we'll talk about what to do in those circumstances later. Make sure you know that Cp is equal to 5/2 times R for a monoatomic ideal gas. So those are the main equations that you need to know for now. There are more equations, but we'll go over that throughout the video. So what exactly is thermodynamics? Thermodynamics is basically, it's associated with the study of heat, mechanical work, and internal energy, and how these three correlate to each other. The first law of thermodynamics is basically this equation. Delta U is equal to Q minus W. U represents the internal energy of a system, and it's proportional to temperature. Q represents the amount of heat that flows into or out of the system. There's basically two ways of transferring energy, and that is through heat and mechanical work. If you apply a force on a box, you can increase its kinetic energy. Or if you add heat to a system, the temperature will go up and the kinetic energy of the molecules will increase. Whenever heat flows into the system, Q is positive. And Q is negative when heat flows out of the system. A positive Q value increases the internal energy of a system because heat is entering into the system. A negative Q value will decrease the internal energy of the system. The next thing you need to know is the signs for work. When work is done by the system, W is positive. Now let's think about that. Imagine if you're doing work, if you're running, if you're exercising, you're burning energy. As you do work, your internal energy will go down. So whenever the system does work, its internal energy decreases. So work is done by the system. W is negative if work is done on a system. That is, if the surroundings perform work on a system. A good example is if you compress a gas. And let's say the system is the gas. Work is being done on the system. The internal energy will increase. Now, if the gas expands, then it's doing positive work. And so its internal energy decreases. Now, let's work on this particular practice problem. For each of these questions, make sure you pause the video and work on these problems yourself. That's the best way you're going to learn thermodynamics. Calculate the change in internal energy. The system absorbs 300 joules of heat and performs 500 joules of work. So let's say this box represents the system. Now 300 joules of energy enters the system. That means the internal energy should go up by 300. And also, the system performs 500 joules of work. Now, because heat is flowing into the system, we know Q is positive 300. If work is done by the system, that means that the work is positive. So using the equation delta U is equal to Q minus W, this is going to be 300 minus 500. So the change in internal energy is negative 200 joules. Now let's make sense of this. Heat flows from the surroundings into the system, and 300 joules of heat flows into it. And the system performs work. To do work, it has to expend energy, so to lose in 500 joules of energy. So therefore, we can see that the net change is 200. It took in 300 joules as heat, and it lost 500 joules by means of doing work on its surroundings. Now what about part B? The system absorbs 720 joules of heat energy, and the surroundings perform 300 joules on the system. So is Q positive or negative in this particular example? Since heat is absorbed, Q is positive. Now what about W? Is it positive or negative? Well, the surroundings perform 300 joules of work on the system. So work is done on the system, and therefore W is negative whenever that's the case. So using the equation, delta U is equal to Q minus W. It's going to be 720 minus negative 300, which is the same as 720 plus 300, and that's equal to 1,020 joules. Now what about part C? What is W in this problem and what's Q? 400 joules of work is done on the system. So is W positive or negative? Just like before, anytime work is done on the system, W is negative. Now the system loses 225 joules of heat energy. So Q is negative because heat went from the system to the surroundings. Anytime the system loses heat or releases heat into the surroundings, Q is negative. So now using this equation, it's going to be negative 225 minus negative 400, which is the same as negative 225 plus 400, which is positive 175. So the internal energy of the system went up because more work was done on a system compared to the amount of heat energy lost by the system. So the system gained a net of 175 joules of energy. Now, what is the difference between an open system, a closed system, and an isolated system? In an open system, matter can enter into and out of the system. So let's say like oxygen gas. It can flow into the system and out. In addition, energy can flow into or out of the system. So heat can flow into or out of an open system. In a closed system, matter cannot enter or leave in a closed system. So oxygen gas, O2, will not be able to enter. However, heat can flow into or out of a closed system. So in an open system, matter and energy can flow into and out of it. But in a closed system, energy can flow into or out of it, but not matter. Now, in an isolated system, no energy or matter can flow into or out of an isolated system. So because heat can't flow into it, Q is equal to 0. And no type of energy can enter into the system, so that means that there can be no work done on a system or by the system. So W is 0, which means that the internal energy is constant. So the change in internal energy of an isolated system is always 0. So keep that in mind. The equation delta U is equal to Q minus W typically applies to a closed system where energy can enter into or out of it. For an open system, you have to take into account the amount of matter that enters or leaves the system. But this equation usually applies to a closed system. Let's try this problem. How much work is required to compress a monoatomic ideal gas at a pressure of 2.5 times 10 to the 5 pascals from an initial volume of 0.015 cubic meters to a final volume of 0.01 cubic meters? So is this an isochoric process, isobaric, adiabatic, or isothermal process? Notice that the pressure is constant. As a result, this is an isobaric process. Now, what exactly is an ideal gas? Some gases behave almost ideally, others do not. Basically, if a gas behaves in a way that fits this equation nicely, it behaves almost ideally. This is the ideal gas law equation. Pressure times volume is equal to the moles of the gas times R times the change in temperature. Now, what about a monoatomic gas? What is that exactly? The word or the prefix mono means one. A monoatomic gas is a gas that contains molecules that have a single atom. So noble gases such as helium, argon, neon, these are monoatomic gases. Diatomic gases contain molecules with two atoms. The word di is associated with two. So oxygen gas, nitrogen gas, hydrogen gas, these are diatomic. Poly means many. Polyatomic gases have molecules with many atoms. Sulfur dioxide has a total of 3 atoms. 1 plus 2 is 3. Sulfur trioxide is a polyatomic gas. Carbon dioxide too. These are gases with many atoms. Now here's another question for you. The gas is being compressed. Do you predict the sign of W to be positive or negative in this case? Anytime a gas expands, the work done by the gas is positive. During gas compression, the work is done on the gas by the surroundings, so therefore the work is negative. So our final answer for the first part of this problem should be negative. So what equation can we use to calculate the work required to compress this gas? Now earlier in the video, I mentioned that for isobaric processes, the work is equal to the pressure times the change in volume. But let's derive that equation. So let's say if we have a gas trapped in this rectangular solid. And let's say this solid has a movable piston. And here's the gas. Now, if we apply, let's say, a force to compress the gas, the piston is going to move a certain distance. Let's call it delta D. Now, the work done to apply a force to move any object is simply the force times the displacement. And anytime you apply a force over a certain area, you're applying a pressure. Pressure is equal to force divided by area. So if we multiply both sides by A, we can see that the pressure times the area is equal to the force. So therefore we can replace F with P times A. So the work is therefore equal to the pressure times the area times the displacement, or the distance that the piston moves to compress the gas. Now, for a rectangular solid, volume is equal to the length times the width times the height. And we know that the area of a rectangle is length times width. So we can view the volume as being the area times the height. And you can think of the height as being the change in the displacement of the piston. So we could say V is equal to A times delta D. So therefore we can replace this term with delta V. So that's how we can come up with the equation work is equal to P times delta V. Now let's draw a PV diagram for this isobaric process. This is a graph that contains pressure and volume. We're going to put pressure on the y-axis, volume on the x-axis. So the pressure is at 2.5 times 10 to the 5 pascals. And we have two volumes. The lower value is 0.01 and the higher value is 0.015 cubic meters. Now because the gas is being compressed, we're going to start at the higher value and travel towards the lower value. Let's call this position A and position B. So we're going to travel from A to B. It turns out that the area of the PV diagram is equal to the work done on the gas or by the gas. So the work is equal to the area. Now we know that the area is equal to the length times the width. The length of this rectangle is basically the pressure. And the width of the rectangle is the change in volume. It's the final volume minus the initial volume. So we can say the width is equal to delta V, the change in volume. So therefore, another way to get the equation for work for this particular PV diagram is equal to the pressure, which is L, times the width, or the change in volume. So that's another way in which you can derive this equation from the PV diagram. So sometimes you need to use the fact that the work is equal to the change in area. It's going to help you to calculate the work for problems that you'll see later in this video. But now let's finish this problem. So W is equal to P delta V for an isobaric process. And the pressure is 2.5 times 10 to the 5 pascals. The change in volume is the final volume, which is 0.01 minus the initial volume of 0.015. And the units for that is cubic meters. Now, you need to pay attention to the units. 1 pascal times 1 cubic meter is equal to 1 joule. Sometimes you might see the units liters and ATMs. 1 liter times 1 ATM is equal to 101.3 joules. So you don't need to convert ATM into pascals and liters into cubic meters. You can simply multiply these two and convert it once into joules if you ever get a question like that. Now for those of you who want to convert ATM into pascals and liters into cubic meters, here are the conversion factors that you need to know. 1 ATM, 1 atmospheric pressure, is equal to 1.013 times 10 to the 5 pascals. And 1 cubic meter is equal to 1,000 liters. So you may or may not need those conversions, but you have them now just in case if they ever become important in the future. But now let's go back to this problem. So if you type this in exactly the way you see it in your calculator, you should get negative 1250 joules. And we could see why it's negative because the gas is compressed by an outside force. So now that we have the work done on the gas, what is the change in the internal energy of the system? Now we have the heat, and heat is being released by the system. So Q is negative 350. So we can use the equation delta U is equal to Q minus W. So that's negative 350 minus negative 1250, or negative 350 plus 1250. So therefore, the change in internal energy is positive 900 joules. Let's try this problem. How much work does a gas perform at a constant pressure of 8.4 atm as it expands from a volume of 2 liters to 4.5 liters? So under constant pressure conditions, we can use this equation once more. Work is equal to pressure times the change in volume. So the pressure is 8.4 atmospheres, and the volume changes from final minus initial 4.5 minus 2.0 liters. So this is equal to 21 liters times atm. Now typically you want your answer to be in joules, so let's convert it. As we mentioned before, there's 101.3 joules per 1 liter times 1 atm. Notice that because the gas expanded, the work done by the gas is positive. The final answer is 2,127 joules. .5 moles of an ideal gas is heated at constant pressure from 30 Celsius to 150 Celsius. Calculate the work performed by this gas. Draw a PV diagram for the process as well. So the equation that we can use is this equation. Work is equal to N times R times delta T. Now keep in mind, PV is equal to nRT. This is the ideal gas law equation. So therefore, the pressure times the change in volume must be equal to nR times the change in T. So if work is equal to P delta V, then it's also equal to nR delta T. N is the number of moles. We have 4.5 moles of an ideal gas. R is the energy constant for a gas. It's 8.3145 joules per mole per Kelvin. Now the temperature difference in Celsius is equal to the temperature difference in Kelvin. Anytime you have a delta T value, it can be in Kelvin or Celsius. The change in temperature, 150 minus 30, is 120. So the Kelvin difference is 120. Notice that the units will be in joules. So let's multiply these three numbers. So the final answer for this problem is 4,400, and if you round it, 90 joules. Now the work is positive because as you heat the gas, it will expand. According to Charles' law, whenever you increase the temperature of a gas at constant pressure, the volume of that gas must increase. So now let's draw a PV diagram. Now that we know the volume is increasing, we can know which direction in the PV diagram we're moving towards. So here's the pressure, here's the volume. And the current pressure is about, we don't know what the current pressure is. So let's just call it P0. Now we don't know what V1 or V2 is equal to, but we can just call it V1, V2. We do know the volume is increasing. So if we call this point A and point B, at point A, the temperature is 30 degrees Celsius, and at point B, it's 150. To increase the volume, you have to increase the temperature, or at least that's one way in which you can increase the volume. So imagine if you have a cylinder with a movable piston, and then you have a gas inside, which is at 30 degrees Celsius. If you add heat to this gas, particularly at a slow rate so that the pressure is constant, the temperature of the gas will increase. And as that happens, the volume will increase. The gas will exert a force that will push up the piston against the atmospheric pressure. And as the volume increases, the gas is performing work against the surroundings. So anytime you heat up a gas at constant pressure, the volume will increase. The pressure of a gas inside a rigid 2.4 liter cylinder is decreased from 4.8 to 3.4 atm. So how can we accomplish this? Well, let's say if we have a metal rigid cylinder and there's a gas inside. And let's say the temperature of this gas is 300 Kelvin. And at this temperature, let's say that the pressure is 4.8 atm. Now the volume is constant because we have a rigid cylinder. The cylinder has a fixed volume of 2.4 liters. So therefore this is an isochoric process. Under constant volume, the only way to really decrease the pressure is to decrease the temperature. If the air of the surroundings, let's say if it's less than 300 Kelvin, let's put it at 200 Kelvin, heat is going to naturally flow from hot to cold. So heat energy is going to leave the gas into the colder surroundings. And as that happens, the pressure will decrease. The relationship between pressure and temperature under constant volume conditions is this. This is, I believe it's called Gay-Lussac's law. Temperature and pressure are directly related. So we can use this equation to calculate the new pressure or the new temperature, whichever we need. But we don't need to do all of that for this problem. Whenever you have an isochoric process, you need to know that the work is always equal to 0 whenever the volume is constant. For one thing, if you use the equation work equals P delta V, the change in volume is 0, so the work has to be 0. That's one way you can look at it. Also, if you draw the PV diagram, we have a pressure of 4.8, and it's decreasing to 3.4 at a constant volume of 2.4 liters. So we're going from position A to position B. Notice that this graph has no area. Because the area is 0, that is the area between this curve and the x-axis, since there's no area, the work is therefore equal to 0. So for any isochoric process, W is always equal to 0. How much heat energy is required to increase the temperature of 7 moles of each of the following gases by 50 Kelvin? So first we have helium at a constant volume of 5.4 liters. Perhaps in an earlier chapter you've learned that Q is equal to MCAT, where M is the mass, C is the specific heat capacity, and delta T is the temperature. Q can also be used in terms of moles. It's equal to N C times delta V, where C is the molar heat capacity. At constant volume, you want to use CV, the molar heat capacity measured at a constant volume process. And under constant pressure conditions, you want to use CP, the molar heat capacity at constant pressure. Now, what exactly is CV for helium? We see we have an isochoric process, the volume is constant, but what is CV for HE? How can we find it? Well, the first thing you should do is look it up in your textbook. Helium has a value of 12.47 joules per mole per Kelvin. Now, if you don't have this value, you can estimate it using this equation. CV is approximately equal to 3/2 times R for a monoatomic ideal gas. Now let's see how close the answer is going to be, or the CV value, rather. So R is 8.3145. And let's multiply that by 3 and divide it by 2. This is equal to 12.472, which is very close to this value. So for most monoatomic gases, CV equals 3/2 R is a good approximation of the actual value. So chances are, for a question like this, you probably won't be given the CV value. You just have to know that CV is equal to 3/2 times R for a monatomic gas. So now let's use the equation. Q is equal to NCV delta T. So we have 7 moles of gas. CV, let's use 12.47. And delta T, the change in temperature, is 50 Kelvin. So Q is equal to positive 4,364.5 joules. A positive Q value is typically associated with an increase in temperature. So the change in temperature is going to be positive when Q is positive. Now, what about part B? At a constant pressure of 9.2 atm. By the way, if you have the change in temperature, you really don't need to use the value of the volume or the value of the 9.2. It's only important if you don't know the change in temperature. So for part B, Q is going to be equal to N times Cp times delta T. So what is Cp for a monoatomic gas? Argon is a monoatomic gas. It's a gas that is composed of particles that have only one atom. N2 is diatomic gas, 2 atoms per single molecule. Now, we said that CV is 3/2 R for a monoatomic gas, but Cp is going to be 5/2 times R. The actual value for argon is about 20.78. And if we take 5/2 and multiply it by 8.3145, this will give us 20.786, which is still pretty close to this number. So for monoatomic gases, make sure that you know that Cp is equal to 5/2 times R. Because if you don't have access to a table, or if this value is not provided, you have to use this fact to calculate Cp. So Q is going to be 7 times 20.78 times delta T, which is 50 Kelvin. So this is positive 7,273 joules. Now what about part C, where we have a diatomic molecule, or part D, where we have a molecule with 3 atoms? What can we do? So let's review. So CV is equal to 3 over 2 times R for a monatomic gas. That is a gas basically with 1 atom in a molecule or in a particle. For diatomic gases, it's approximately equal to 5 over 2 times R, and nitrogen fits that description. Now, for polyatomic gases with 3 molecules, it turns out that it's approximately 7 over 2 times R. However, at this point it begins to deviate, so let's use an approximately equal to symbol. So CO2 would fit this example. It has 3 atoms per molecule. Now for CP, it's different. CP is 5 over 2 times R for a monoatomic gas. It's 7 over 2 times R for a diatomic gas like N2. And it's approximately 9 over 2 times R for a gas that has 3 atoms, or triatomic. So now let's go back to N2. If you look up in your textbook the values for CP and CV for N2, you'll see that CV is 20.76 and CP is 29.07 for N2. At least that's according to the textbook that I have. So for a diatomic gas, we said it's 5 over 2 times R. So if you take 8.3145 multiplied by 5 and divided by 2, this is going to give you 20.786, which we calculated that earlier. And as you can see, it's not exactly the same, but it's still pretty close. So for monoatomic gases and diatomic gases, you can use these equations to get a good approximation. For CP, it's 7 over 2 times R. So 8.3145 times 7 divided by 2 is about 29.1, which is still a good approximation for CP. Once you start having molecules with 3 atoms, then it begins to deviate. But let's finish part C. So Q is going to be N times not CP, but we're going to use CV since we want to find out how much heat is required to increase the temperature at constant volume. So it's going to be 7 times 20.76 times 50. And this is 7,266 joules. Now for part D, CO2, let's talk about the values of CV and CP. CV for CO2 is about 28.46, and CP is equal to 36.94. So now if we approximate CV using the equation 7 over 2R, this is going to be 8.3145 times 7 divided by 2, and that's 29.1. As you can see, there's a slight difference between these two values. You might be maybe 2% off, but it's still pretty close. So if you don't have the actual value of CV for CO2, go ahead and use this approximation. But if you have it, preferably use this one. Now for CP, it's approximately 9 over 2 times R. This will give you 37.415. So it's not exactly the same, but it's still close enough. So for part D, Q is going to be N times CP, since we're dealing with constant pressure, times delta T. So it's 7 times 36.94 times the change in temperature of 50 Kelvin. And this is equal to 12,929 joules. The temperature of a sample of ideal gas increased from 300 Kelvin to 500 Kelvin. Calculate the change of the internal energy if there were 5 moles of a monoatomic gas. Anytime you want to find a change in the internal energy of the system, you can use this equation. Delta U is equal to N CV delta T. Now, keep in mind, for a monoatomic ideal gas, the CV value is 3 over 2 times R. So delta U is equal to N, or simply 3 over 2 NR delta T for a monoatomic ideal gas. So it's going to be 3 over 2 times 5 moles. R is 8.3145. And the change in temperature, final minus the initial value, that's 500 minus 300, which is a change of 200 Kelvin. And this is going to be equal to 12,472 joules, rounded to the nearest whole number. Now what about part B? For part B, we can use the same equation, but for a diatomic gas, CV is equal to 5 over 2 times R. So therefore, for a diatomic gas, we have the equation 5 over 2 NR delta T. In this part, N is going to be 8, R is 8.3145, and delta T is still 200 Kelvin. So this is equal to 33,258 joules. How much work is required to compress 7.5 moles of an ideal gas at 400 Kelvin from 5.2 liters to 2.1 liters? So what type of process do we have? And let's begin by sketching a PV diagram. Notice that the temperature is constant. Under constant temperature conditions, we have an isothermal process. And during an isothermal process, the change in internal energy is 0. So that's the answer for the second part of the problem. Keep in mind, delta U is always equal to N CV delta T for any process. So for an isothermal process, delta T is 0, which means that delta U has to equal 0. Now, just because the temperature is constant doesn't mean Q is 0. Heat can still flow into the system or out of the system. It just happens in such a way that the temperature remains constant. Now, during an isothermal process, as the volume of the gas increases, the pressure will decrease. Now, it's not going to decrease like this. According to Boyle's law, it's going to decrease more like that. It's not a straight line, it's actually curved. But how can we calculate the work required to compress this particular gas? So if the gas is being compressed, let's say if we're going from position A to position B, we're going this way. As you travel towards the left of a PV diagram, the work done is going to be negative. Anytime you're compressing a gas, W is negative. Anytime the gas expands, W is positive. Now the work done is going to be equal to the area under the curve. So how can we calculate this particular area? It doesn't look like a rectangle, so we can't use the area equation, which is length times width. To get the formula that you need to use calculus. The work required, which is the area under the curve, is simply the antiderivative of the pressure function using volume as a differential. So it's the antiderivative of P dV. Now, according to the ideal gas law equation, PV is equal to nRT. Now let's get P as a function of V. So if we divide both sides by V, P is equal to nRT divided by V. So therefore we have this equation. We can now replace P with nRT over V. Now since the differential is based on the variable V, we're going to treat nRT as constants, so we can move it in front of the integral. So the work is going to be nRT times the antiderivative of 1 over V dV. Now for those of you who have taken calculus, you know that the antiderivative of 1 over x is equal to ln x. For those who haven't taken calculus yet, just sit back, relax, and then you'll see the equation that you need in order to solve this problem. But I'm just going to go over the steps to get that equation. So if the antiderivative of 1 over x is ln x, the antiderivative of 1 over v is going to be the natural log of v evaluated from position A to position B, which position A was the initial volume and position B was the final volume. So it's going to be nRT. We need to plug in these two values, the final value minus the initial value. So it's nRT ln V final minus nRT ln V initial. Now, if you recall from your algebra class or pre-calculus class, the natural log of A minus the natural log of B can be rewritten as ln A divided by B. So therefore, we can combine these two expressions as a single log. So the equation that we need for this problem is nRT natural log V final divided by V initial. Now let's finish this problem. N is the number of moles, which is 7.5. R is the energy constant for gases, 8.3145. T is the temperature, 400 Kelvin. And then this is going to be ln V final, which is 2.1, divided by V initial, and that's 5.2. So in this problem, W is negative 22,617 joules. And we can see why it's negative, because the gas is being compressed from a high volume to a low volume. So that's how you can calculate the work for an isothermal process. Now what about the heat? We know that the internal energy, the change in the internal energy, is 0. But how can we calculate the heat transferred during this process? Well, one equation that you can use is delta U is equal to Q minus W. If we add W to both sides, we can see that Q is delta U plus W. And since delta U is 0, Q is equal to W. So Q is also negative 22,617 joules. That's how much heat is transferred. So basically, let's understand what's happening in this situation. Consider a cylinder with a movable piston, and let's say that we have a gas inside. Now, as work is being done on the gas to compress it, so work is negative, we can see that the volume is decreasing. The gas is releasing heat into the environment. Now, this is occurring at such a rate that the temperature remains constant. So the energy that's going into the system to compress the gas is leaving the system as heat. So 22,616 joules of work goes into the system to compress the gas. So that action increases the internal energy by that amount. However, heat leaves from the gas, and about 22,616 joules leave the gas at the same time. So that decreases the internal energy. So therefore, the change in internal energy is 0. The amount of energy that is being transferred into the gas by means of the mechanical work is equal to the amount of energy that leaves the gas by means of heat. So the gas gains no internal energy. The internal energy remains constant in this particular problem. 3.2 moles of an ideal gas expands from a pressure of 5 atm to 1.4 atm at a constant temperature of 127 degrees Celsius. Is work done by the gas or on the gas? Anytime a gas expands, the work is positive. And whenever the work is positive, work is done by the gas on the surroundings. So now how can we calculate the work for this problem? Once again, the temperature is constant, so we have an isothermal process with a PV diagram that looks like this. So this time, we're traveling towards the right. Anytime you travel towards the right of a PV diagram, the work done is positive. Now, this problem is slightly different from the last one because in the last problem, we had 2 values for volume, but here we have 2 values of pressure. So what can we do in this problem? Well, let's start with this equation. W is equal to nRT, natural log V final divided by V initial. For an isothermal process, since temperature is constant, whenever you increase the volume, the pressure will decrease. According to Boyle's law, P1 V1 is equal to P2 V2. So we could say P initial times V initial is equal to P final times V final. Now let's divide both sides by V initial and also by P final. If we do that, notice what happens. V initial cancels on the left side, P final cancels on the right side. So therefore, P initial divided by P final is equal to V final divided by V initial. So we can replace V final over V initial with P initial over P final. So therefore, this is the equation that you want to use for this problem. So during an isothermal expansion or compression, you can use this equation. W is equal to nRT ln P initial divided by P final. So now let's finish the problem. N in this problem is 3.2 moles. R is still 8.3145. Now, the temperature has to be in Kelvin. If you have any equation where you just see T, like in PV equals nRT, or this equation, it has to be in Kelvin. But for equations where you would see the term delta T, it can be in Kelvin or Celsius. Just keep that in mind. So to get the Kelvin temperature, we need to add 273 to 127. Which is about 400 Kelvin. Let's multiply that by the natural log of the initial pressure, which is 5 atms, divided by the final pressure of 1.4. So the work done should be positive, and it's done by the gas. So the answer to this problem is positive 13,548 joules. Now, as you mentioned before, for an isothermal process, delta U is equal to 0, and Q is equal to W. So therefore, the system absorbed 13,548 joules of heat energy, and at the same time, it used that energy to perform 13,548 joules of work. So the energy that entered the system as heat left it by means of mechanical work. An ideal monoatomic gas expands from 2.5 liters at 300 Kelvin to 8 liters at a constant pressure of 3 atm. What is the temperature when the volume is 8 liters? So let's draw a PV diagram. Now the first thing we want to do is identify what type of process we have. And it turns out that this is an isobaric process, since the pressure is constant. The volume changes from 2.5 liters to 8 liters. And the pressure is always at 3 atm. So the work has to be positive since we're traveling towards the right of the PV diagram. So we're going from position A to position B. At position A, the temperature is 300 Kelvin. We need to calculate the temperature at position B. So how can we do that? Well, we can use this equation. V1 divided by T1 is equal to V2 divided by T2 under constant pressure conditions. This is known as Charles' law. V1 is 2.5 liters. T1, the temperature that corresponds to it, is 300 Kelvin. So we want to find a new temperature at a volume of 8 liters. So let's cross multiply. 300 times 8 is 2400. And this is going to be equal to 2.5 times T2. So 2400 divided by 2.5 will give us a temperature of 960 Kelvin. Now what about part B? How many moles of gas are present? Let's use the equation PV is equal to nRT. The pressure in this problem is 3 atm. Now we can use point A or point B. Let's focus on point A. At point A, the volume is 2.5 liters. We're looking for N. R is going to be 0.08206. Now the R value that you want to use in this equation is dependent on the units of P and V. There's two R values that you need to be aware of. You've seen this one, 8.3145. joules per mole per Kelvin. If you're going to use this R value, the pressure has to be in pascals and the volume has to be in cubic meters, because 1 pascal times 1 cubic meter is equal to a joule. Now the other R value, which is the one that we're using, 0.08206, it has the units liters times ATM divided by moles times Kelvin. And since the pressure is in ATM and the volume is in liters, this is the R value that we want to use in this equation. T at point A is 300 Kelvin. If you use the values at point point B, you should get the same answer. So let's calculate N. It's going to be 3 times 2.5 divided by 300, and then take that result divided by 0.08206. So you should get 0.30466 moles. Now let's calculate the work performed by this gas. So we can use the equation W is equal to NR delta T. So we have N, which is 0.30466. Now for R, I'm going to use 8.3145 because I want my answer to be in joules. And delta T, the change in temperature, the final minus the initial temperature, that's 660 Kelvin. So multiplying these three numbers will give us a value of 1672 joules. So that's how much work is performed by this gas. Now keep in mind, you can also use this equation. W is also equal to P delta V under constant pressure conditions. So the pressure is 3, the change in volume, the final minus the initial volume, that's 8 minus 2.5, which is 5.5 times 3. That's equal to 16.5 liters times ATM. Now, you need to convert this to joules. So we need to multiply by 101.3 joules per liter per ATM. And if you do that, you should get approximately around 1671 joules, which is pretty close to this answer. By the way, keep in mind this answer is rounded. Now, how can we calculate the change in the internal energy of the system? To do that, the equation that we need is delta U is equal to N CV delta T. This is true for any process, so make sure you keep this equation in mind. So N is still 0.30466. Now we have a monoatomic gas, so CV is 3/2 times R. That's 3/2 times times 8.3145. We want delta U to be in joules, and the change in temperature is 660 Kelvin. So this gives us a value of 2,508 joules. So that's the change in the internal energy of the system. So now how can we answer part D? How much heat energy was transferred? Well, there's different ways in which we can do that. So first, let's make some space. One equation that we can use is the equation that is associated with the first law of thermodynamics. Delta U is equal to Q minus W. Therefore, Q is delta U plus W, since we have those two values. Delta U is 2,508 and W is 1672. So therefore, the amount of heat transferred is about 4,180 joules. Now, this is not the only way in which we can get this answer. We can also get it using other equations as well. You can use this equation, Q is equal to N Cp delta T. So N is still 0.30466. Cp for a monoatomic gas is 5/2 times R. And delta T is 660 Kelvin. So this will also give you 4,180 joules, rounded to the nearest whole number. So that's how you can find Q if you have the change in the internal energy and if you have the work, or you can also find it in terms of temperature, or you can find it in terms of pressure and volume. So let me give you a third equation that might be useful if you don't have the temperature. And it's Q is equal to P times Cp delta V divided by R. By the way, this equation only applies to processes dealing with constant pressure, that is isobaric processes. And this equation also applies to isobaric processes. So if you have that chart that I gave you earlier, it might be good to expand that chart and add these equations to the isobaric row. I couldn't fit all of the equations that I had on the screen, so I'm going over it now. So let's plug in the values that we have. So P, which is constant, is 3 atm, and Cp, that's going to be 5/2 times R. Since we have a monoatomic gas at constant pressure. And delta V is 8 liters minus 2.5, so that's a change of positive 5.5. Let me get rid of something first, since this is in the way. Now, I really don't have to plug in the R value, because as you can see, R will cancel. So therefore, it's going to be 3 times 2.5, which is 5/2, times 5.5. Now, this answer is in liters times atm, because pressure was in atm and the volume was in liters. So we need to convert it. So as of now, you should get 41.25 liters times atm. So we need to multiply by 101.3 joules. And if you do that, you should get about 4,179. As you can see, these answers are very, very close. So that's how you can calculate the heat transferred in terms of pressure and volume, instead of using temperature. So you have many different ways in which you can calculate Q. But now let's talk about how we can derive that equation. So it comes from this equation, Q is equal to N Cp delta T. Now we know that PV is equal to nRT, the ideal gas law equation. And in this problem, the pressure is constant, but the volume is not constant. The volume changes. So therefore, we could say that P delta V is equal to nR delta T. Since pressure is constant, only volume and temperature is changing. So I added a triangle to only that portion of the equation. Now we need to solve for delta T. So P delta V divided by nR is equal to delta T. So now let's replace delta T with this value. So Q is equal to N times Cp times P delta V divided by Nr. So we can cancel N. So therefore Q is equal to P, the pressure, times Cp, the molar heat capacity at constant pressure, times the change in volume divided by R. So keep in mind Cp is equal to 5 over 2R for a monoatomic gas. For a diatomic gas, it's 7 over 2R. And if you have a gas with 3 atoms, it's going to be 9 over 2R approximately. So you can use that estimation if you don't have the exact value. But if you can look up the value in your textbook for that particular gas molecule, make sure you use that value because it's more accurate. 700 joules of work was done on an ideal gas in a perfectly insulated container. How much heat energy was transferred? So first, is the work positive or is it negative? Since work is done on the gas, the work is negative 700 joules. Anytime work is done on the gas undergoes compression. Now, what type of process do we have? Is this an isobaric process, isochoric, adiabatic, or isothermal? The key expression here is the gas is contained in a perfectly insulated container. So if it has good insulation, it's going to be difficult for heat to flow into or out of the system. So therefore, Q is equal to 0. If heat energy cannot flow into or out of the system, Q is 0, which means that we have an adiabatic process. So the answer to part A is 0. Now what about part B? Well, delta U is equal to Q minus W. Since Q is 0, for an adiabatic process, delta U is negative W. And W is negative 700, which means delta U is equal to positive 700. So in an adiabatic process, the work performed on a gas goes directly to change its internal energy. So 700 joules of work was done on a gas. As a result, the internal energy went up by 700 joules. Now, will the temperature increase or decrease? Well, delta U is proportional to delta T. So if delta U is positive, delta T will be positive, which means that the temperature will increase. So anytime you have an adiabatic compression, the temperature will go up. And during an adiabatic expansion, the temperature will go down. So as we compress the gas adiabatically, the net effect was to increase its internal energy, and therefore the temperature went up. Let's work on this one. 3 moles of neon gas expands adiabatically against a piston, and the temperature drops from 800 Kelvin to 500 Kelvin. What is the change in the internal energy of the system, or of the gas? To find the change in the internal energy, we can use this equation, NCV delta T, which applies to any process. So N is 3 moles. Now neon is a monoatomic gas, so CV is equal to 3 over 2 times R. So that's 3 over 2 times 8.3145. And delta T, the change in temperature, 500 minus 800, so it drops by 300 Kelvin. So delta T is negative 300. So delta U is negative 11,225 joules. Part B. The amount of heat transferred during any adiabatic process is always 0. So in this case, delta U is equal to negative W, which means that W is equal to negative delta U. And if delta U is negative 11,225, that means the work done by the gas is positive 11,225 joules. Anytime a gas expands, the work done by that gas is equal to a positive value. Let's try this problem. We have 0.5 moles of a diatomic gas, particularly nitrogen gas, and it's placed inside a 5.0 rigid container at a pressure of 2 atm. This gas is heated until it reaches a pressure of 8 atm. So let's begin by drawing a PV diagram. So the volume is 5.0 liters. The initial pressure is 2 atmospheres, and it increases to 8 atmospheres. Notice that this is an isochoric process. The volume is constant since the gas is contained in a fixed, rigid 5.0 liter container. For an isochoric process, the work done by the gas is 0. So no work is done in this process. So how can we calculate how much heat energy will be absorbed by the gas? Particularly in terms of pressure and volume. An equation that you can use is this one. Q is equal to V times CV times delta P divided by R. The volume is 5 liters. CV is 20.76. The change in pressure, 8 minus 2, so that's an increase of 6 atm, and R is 8.3145. So this gives us a value of 74.9. But V has the units liters, P has the unit atm. So we need to multiply this number by 101.3 to convert it to joules. So the answer is about 7,588 joules. So that's how much heat energy is absorbed in the process. And we know that delta U is Q minus W. And since W is 0, delta U is equal to Q in this problem. So as a result, delta U is also 7,588. Now we know that delta U is always equal to this equation, NCV delta T. So you can also find Q using that equation. So N is 0.5, CV is 20.6. The only thing we're missing is delta T, which we can find that as we work on part B. I should have kept this. So what is the temperature when the pressure is 2 atm and when the volume is 5? So how can we find it? Well, let's go back to the ideal gas law equation. PV is equal to nRT. So at point A, the pressure is 2 atmospheres, the volume is 5 liters, N is 0.5, R is 0.08206, and we could solve for T. So it's going to be 2 times 5, which is 10, divided by 0.5, which is 20, divided by 0.08206. So at point A, the temperature is 243.7 Kelvin. And then let's do the same for point B. This time the pressure is going to be 8 instead of 2. So basically, if the pressure is increased by a factor of 4, the temperature should be increased by a factor of 4. So if we multiply 243.7 times 4, it should be about 974.8. But that answer is a rounded answer because I rounded this answer. So let's use the equation. 8 times 5 divided by 0.5, that's 80, divided by 0.08206. So that's 974.9 Kelvin. So now we can find the heat transferred using the other equation. So delta T is going to be the final temperature, which is 974.9 Kelvin, minus the initial temperature of 243.7 Kelvin. So delta U, which is equal to Q in this particular process, is positive 7,590 joules, which is very, very close to the other answer of 7,588 joules. So as you can see, you can find Q if you have the change of temperature using this equation for a constant volume process, or if you have the volume and the pressure, you can use this equation. Q is equal to V CV delta P divided by R. But now let's talk about how we can derive that equation, because it really comes from this equation, N CV delta T. Now, using the ideal gas law equation, PV equal nRT, we need to replace delta T with something. Now, in this problem, the volume is constant, so the pressure is changing. So delta P times V is equal to nR delta T. So solving for delta T, it's delta P times V over nR. So let's replace delta T with this value. So it's going to be NCV delta P times V over nR. So Q is equal to the volume times the molar heat capacity measured at constant volume times the change in pressure divided by R. So that's how you can find Q if you have an isochoric process and if you're given the volume and the two different pressure values. If you have the change in temperature, then it's easier to use this equation. And also keep in mind that Q is equal to delta U for any isochoric process, since W is equal to 0. So make sure you write these down in your chart so you can organize all of the equations you need for the different types of processes that you'll see on your exam. An ideal monoatomic gas is compressed from 12 liters to 3 liters at a constant pressure of 2.5 atm. Heat is added to increase the pressure at constant volume until the temperature reaches its original value. Calculate the total work done by the gas and the total heat flow into the gas. And also draw a PV diagram. So let's do that first. So we're starting at high volume, a volume of 12 liters, and the volume is decreasing to 3 liters at a pressure of 2.5 atm. So we're going this way. Let's call this position A, position B. So that's an isobaric process. Now heat is added. If heat is added, the temperature will increase and the pressure will increase as well. And this occurs at constant volume, so that's an isochoric process. So we need to go up in the PV diagram. And then the temperature will reach its original value. calculate the total work done by the gas and the total heat flow into the gas. Let's call this position C. So what can we do in this problem? How can we figure out the answer? Well, we need to calculate the work done as we travel from position A to position C. So let's find it from A to B. So that's an isobaric process, so we can use the equation P delta V. The pressure is 2.5 atm, and the change in volume, the final minus initial, that's 3 minus 12, and then we need to multiply it by 101.3 to convert it to joules. So this is 2.5 times negative 9 times 101.3. So the work done from A to B is negative 2279 joules. Now what about the work done from B to C? From B to C, that's an isochoric process. The volume is constant and the work is always zero. Therefore, the work done from A to C is the sum total of these two values, which is just negative 2279 joules. Now, what about going from A to C? Notice that this is an isothermal path. The key expression is the temperature. The temperature remains at the same value. It reaches its original value. So whatever the temperature was at point A is the same as point C. And for an isothermal graph or process, delta U is equal to 0. So from A to C, the fact that delta U is equal to 0, which means that Q is equal to W. Q is W plus delta U based on this equation, if you rearrange it. So if delta U is 0, Q is equal to W, which is negative 2279. Now let's see if there's another way we can get the same answer by calculating Q through the individual paths. So we need to get negative 2279 during this other technique or other method. So first, let's assign the temperature value to point A. Let's say the temperature is 1000 Kelvin. Now, notice the volume decreased from 12 to 3 liters. Whenever the volume decreases, the temperature decreases as well if the pressure is held constant. The volume decreases by a factor of 4. If you divide 12 by 4, you should get 3. Likewise, if we divide 1000 Kelvin by 4, it should give us a temperature of 250 Kelvin. So that's going to be the relative temperature at point B if point A is 1000 Kelvin. Now at point C, the temperature is 1000 Kelvin because it's back to its original value. But going from B to C, the temperature increases by a factor of 4, which means the pressure must increase by a factor of 4. At constant volume, if you raise the temperature, the pressure will increase. So 2.5 times 4 is 10 atm. Now, how can we calculate Q in the isobaric process from A to B? There's two equations that you can use. You can use this one, Q is equal to N Cp times delta T during a constant pressure, or an isobaric process. Or we can use the other equation, Q is equal to P Cp delta V divided by R. Ideally, we want to use this equation because we have the pressure and the change in volume. We don't have the moles. We do have the temperature, but if we are going to use the first one, we need to find N, which we could do using the equation PV equals nRT. We could find it at any points, point A, B, or C. But we don't have to do that, so let's use this equation. So Q is going to equal P which is 2.5 atm, times Cp, and this is a monoatomic gas. So therefore, Cp is going to be 5 over 2 times R. Cv is 3 over 2 times R. Delta V, the change in volume, final minus initial, is 3 minus 12. And then divided by R. And don't forget, you need to multiply this value by 101.3 to convert it to joules. So it's 2.5 times 5 divided by 2 times negative 9. You should get negative 56.25, and then multiply that by 101.3. So Q from A to B is equal to negative 5,698 joules. Now what about from B to C? How can we calculate Q? So from B to C, you can use this equation. Q is equal to NCV delta T, since the volume is held constant. Or we can use this equation, VCV delta P divided by R. Let's go ahead and use that one. So V is 3 liters from position B to C. It's a constant 3 liters. And CV, that's 3 over 2 times R. And delta P, the change in pressure, final minus the initial value, 10 minus 2.5, that's a change of 7.5, divided by R. And then multiplied by 101.3 to convert it back to joules. So it's 3 times 3 divided by 2 times 7.5. That's 33.75 times 101.3. So this is equal to 3,418.9 joules. Now, to calculate the total heat, which we said was negative 2279 joules, we could simply add the heat absorbed or released by processes A to B and B to C. So if we take negative 5,698 and add it to 3418.9, this will give you negative 2279 joules, which is the same answer that we had before. But now you know how to calculate the heat energy absorbed or released during an isobaric process and an isochoric process. How much work is performed by the gas as the system moves in the cyclic path A to B to C to D to A? Well, a simple way to find the work is to calculate the area. That is the area of the shaded region. So we have the shape of a rectangle, and the area is simply the length times the width. The length of the rectangle, as you can see, is the change in pressure, and the width of the rectangle is the change in volume. The change in pressure is the difference between 1 and 8 atmospheres, so that's 7, and the change in volume, 6 minus 2, so that's 4. And we need to convert it to joules, so we're going to multiply it by 101.3 joules per liter per atmosphere. So the work performed is 2,836.4 joules. Now this answer, is it positive or is it negative? What would you say? It turns out that if you're traveling in the clockwise direction, the work done is positive. Now if you travel in, let's say, the counterclockwise direction, the work done is going to be negative. Now let's prove that. First, we need to prove this answer. To do that, let's calculate the work performed in each step. So let's start with the first step, that is from A to B. So that's an isobaric process. So we can use the equation work is equal to P delta V. And anytime you go to the right, the work done is positive. So the pressure is 8, the final volume is 6 minus 2. So that's 8 times 4, which is 32, times 101.3. So the work done from A to B is positive 3,241.6. Now the work done going from B to C, that's an isochoric process. And as a result, the work is 0. So from B to C and D to A, the work is 0. So now we need to calculate the work going from C to D. So the pressure is now 1. D is the final position. C is the initial position, so it's going to be 2 minus 6. So that's negative 4 times 101.3. And that's equal to negative 405.2 joules. So if we add these two values, 3241.6 plus negative 405.2, this is going to be equal to 2836.4. And if you go in the reverse direction, the numbers will be reversed. Instead of this value being 2 minus 6, it's going to be 6 minus 2. So this is going to be positive 405, and this will be negative 3241.6. You can try it. But going in the counterclockwise direction, the work will be negative 2836.4. That's the answer to the second part of the problem. But for the first part of the problem, traveling in the clockwise direction, the work done is positive. Now, if you want to understand why that's the case, keep in mind, anytime you travel towards the right, the work is positive. And if you travel towards the left, in a PV diagram, the work is negative. As you travel towards the right, notice that the pressure is higher, and therefore the work done by the gas is going to be higher. As you travel towards the left, the pressure is lower, it's 1. And so the negative work performed by the gas is going to be lower. So the net work done is positive, because the higher side is moving towards the right. If you move in towards the left, at the higher pressure, then the overall work is going to be negative. The work is determined by the direction of the system at high pressure, because at high pressure, that's where most of the work will be accomplished. Go ahead, take a minute, pause the video, try this problem, and then unpause it when you want to see the solution. So let's begin by drawing a PV diagram. Now, the volume of a gas increases from 3 liters to 9 liters, and it occurs at a constant pressure of 4 atm, which is lower than 10. So we're traveling in this direction. Let's call this position A and position B, or state A and state B. Next, heat is added to increase the pressure to 10 atm. So that's an isochoric process. Finally, heat is removed to decrease the pressure and volume back to its original values. That is at 3 and 4. And it's going to travel back to the original state in a straight line path. So calculate the total work done in this process. To find the answer, we got to calculate the area under the curve. And this is the area of a triangle, so it's going to be 1/2 base times height. The base of the triangle is the change in volume, and the height of the triangle is the change in pressure. So the change in volume is going to be equal to 6 liters, and the change in pressure is 10 minus 4, so that's a difference of 6, times 101.3 to convert it to joules. So 6 times 6 is 36. Half of that is 18. So the work done is going to be 1,823.4 joules. Now, here's a question for you. Is the work done positive or negative? So notice the direction that we're traveling in. That is, the system is rotating in the counterclockwise direction, which means that work in this process is negative. If it's moving in a cyclic clockwise direction, the work should be positive. But now let's see if we can get this answer by calculating the work done in each individual step. So let's start from A to B. That's an isobaric process, so we can use the equation P delta V. The pressure is 4 at this point. The change in volume, final minus initial, 9 minus 3, that's 6, times 101.3. So 24 times 101.3 gives us a value of 2,431.2. And the work done is positive. Now between B and C, that's an isochoric process. So the work done for that region is 0. Let's see if I can fit it here. Now what about in this section going from C to A? How much work is performed by the gas in taking that route? It turns out that you can use this equation to get the answer, but you have to use it in a certain way. Notice that the pressure is not constant. It changes from 10 to 4. So what value of P should you plug in to this equation to make it work? It turns out that if the pressure increases at a constant linear rate, you can use the average pressure. So the equation for the path to calculate the work from C to A is going to be 1/2 P initial plus P final times delta V. To find the average of these two numbers, you need to add them up and divide by 2. So the average pressure is the initial and the final pressure is the sum of the two values divided by 2, or half of the sum. So using that equation, 10 plus 4 is 14, half of that is 7. So the work is going to be the average pressure of 7 times the change in volume, final minus initial, so 3 minus 9, which is negative 6, times 101.3. So negative 42 times 101.3 gives us a value of negative 4,254.6. Now the reason why it's negative is because we're traveling towards the left of the PV diagram. Here it's positive because we're going towards the right of the PV diagram. Now in terms of the magnitude of these two values, the one at the top is greater because the average pressure is higher than the pressure at the bottom, which is 4. So keep in mind, the direction of the system at high pressure determines the overall sign of the work done for this entire cyclic process. That's why the overall work done is negative, because at the top is moving towards the left. Now let's add these two values. So negative 4254.6 plus 2431.2 gives you this answer, negative 1823.4. Which of the following is not a state function? Pressure, internal energy, work, temperature, volume? Which one? It turns out that work is not a state function. Pressure, internal energy, everything else is a state function. Let's say if we have a PV diagram, and let's say we have 3 points, point A, B, and C. The work that's required to go from A to C by means of B is going to be different than the work required to go from A to C. It's not going to be the same. Let's say A to C is an isothermal path. However, the change in internal energy going from ABC or AC directly is going to be the same. It may not be zero, but it's going to be the same. The change in internal energy does not depend on the path. It depends on the state. As long as you go from A to C, regardless if you pass through this path or this path, the change in internal energy is the same, which means it's a state function. The work will not be the same. The work depends on the path that you take. If you go from A to C by taking this route, the work is different than if you take this route, because the area under the curve is different. Also, heat is not a state function. Now, pressure, temperature, and volume, they will be the same regardless of the path taken. If I take the path A to B to C, the pressure at C will still be the same. Let's say it's 2 atmospheres. If I go from A to C, at C the pressure would still be 2 atmospheres. So as you can see, the pressure is a state function. It depends on the initial and final states. Just like internal energy, it doesn't depend on the path taken. Whereas work and heat, which are forms of energy transfer, they depend on the path taken, and so work and heat are not state functions. Let's try this problem. So let's focus on path A to D to C, which is this path. And we're given the amount of heat that flows into the system. So because heat is absorbed by the system, Q is positive. And we're told that 45 joules of work is done by the system. Whenever the system does work or performs work, the work done is positive. Now in path ABC, the work performed by the gas is 30 joules. How much heat energy is absorbed in path ABC? To answer this question, it's important to realize that internal energy is a state function. The change in the internal energy in going from ABC or ADC is the same. So if we could find delta U for this path, we can use it to find Q in path ABC. Delta U is equal to Q minus W. So that's 125 minus 45, which is 80. So we can use this value for path ABC. Solving for Q, Q is delta U plus W. So that's 30 plus 80. So 110 joules of heat energy was absorbed in path ABC. Now what about the next part? When a system returns from C to A along the curved path, that's the path in the middle, 38 joules of energy is transferred by work. Now this energy transfer, is it positive or is it negative? Anytime a gas is compressed, or if you travel towards the left of a PV diagram, the work done is negative. As you travel towards the right, the work done will be positive. So this is negative 45. Now, in order to find Q, that is the amount of heat energy transferred during this process, we need to find delta U. So how can we do it? Well, we know that going from A to B to C, delta U is positive 80. Going back from C to B to A, it's going to be negative 80. Because the internal energy is a state function, it really doesn't matter the path that you take. As long as you get from A to C, it's positive 80. So going back to C to A, it's negative 80. It's also negative 80 if we take the curved path. The change in the internal energy of a system is independent of the path taken. So delta U going from C to A is going to be negative 80 instead of positive 80. So now we can find Q, which is delta U plus W. So that's negative 80 plus negative 45. Actually, that's not supposed to be negative 45. It's supposed to be 38. I guess I was looking at this number. But going from C to A, 38 joules of energy is transferred by work. So this is negative 38. So if we add these two numbers, this is going to be negative 118. So that's how much heat energy is transferred. Now, because Q is negative, that means that heat was released during this process as the system went from C to A. Now, what about the next part? If UA is equal to 0 and UB is equal to 20, how much heat energy is absorbed in paths AB and BC? Well, first, let's find the internal energy at path C. As we mentioned before, going from A to B to C, the change in the internal energy is 80. So if A is 0, C is 80 joules higher than A. So at C, the internal energy is 80. So with that information, we can calculate Q. Now, the work done for any isochoric process, which is B to C or A to D, is 0. So let's make some space. So W is equal to 0, and it's equal to 0 on this side as well. Now the work going from ADC is 45. So that's here to here. So if A to D is already 0, D to C must be 45. The work done from A to D plus the work done from D to C is equal to work done from A to D to C. So this is 0, this is 45. This other value must be 45. Now what about the work done from A to B? We know the work done from A to B plus that for B to C is equal to work done for A to B to C. Now this is 0, so these two must be equal to each other. So therefore, the work done from A to B is 30. So now that we have these values, we can calculate Q. So focusing on path AB, Q is equal to delta U plus W. Delta U is the difference between these two values. UA is 0, UB is 20, so the change going from A to B is positive 20. Going from B to A must be negative 20. And W is 30. So that means Q AB is equal to positive 50 joules. Now what about from or path B to C? In path B to C, W is 0, but going from B to C, the change in the internal energy is positive 60. It changes from 20 to 80. So final minus initial, 80 minus 20 is 60. So Q is 60. Therefore, QBC is equal to positive 60. And this is in line with QABC, which is 50 plus 60, which is 110. And as we can see, these two are equal to each other. Now what about the last part of the problem? If UD is equal to 30, how much heat is transferred in paths AD and DC? So let's put 30 here. Now let's focus on AD. So Q is delta U plus W. So if we add 0 plus the change, which is 30, we can see that QAD is equal to positive 30. Now what about Q dC? What's the answer for that? Well, notice that the change in the internal energy going from D to C, it increases by 50. 80 minus 30 is 50. And the work done going from D to C is positive 45. So Q is delta U plus W. So 50 plus 45, that's equal to positive 95. Now, if we add 30 and 95, it should give us the total of 125, which it does. So everything is balanced, so to speak. The PV diagram shown below applies to 2.1 moles of an ideal diatomic gas. Calculate the temperature at all points. Now we need to use the equation PV is equal to nRT, at least for the first point. And then we can easily find the other points. Now notice that the volume is in cubic meters. 1 cubic meter is equal to 1,000 liters. So to convert these values into liters, multiply by 1,000. So this is basically 10 liters, and this is equivalent to 50 liters. Now let's calculate the temperature at point A, since that temperature is going to be the lowest temperature. The temperature increases whenever you move in this general direction. The temperature increases as you go towards the right in a PV diagram, and it increases as you go up in a PV diagram. So using this equation, at point A, the pressure is 5 atmospheres, the volume is 10 liters, we have 2.1 moles, R is 0.08206, and we're looking for T. So 5 times 10 is 50, divided by 2.1, and then take that result, divided by 0.08206. So the temperature at point A is 290 Kelvin. Now what about the temperature at point D? Notice that the volume increases from 10 liters to 50 liters. If you increase the temperature at constant pressure, the volume will increase proportionally. So the volume increased by a factor of 5, which means the temperature should also increase by a factor of 5. 290 times 5 is equal to 1450 Kelvin. Now if you want to, you can use the PV equals nRT equation to get that answer. If you plug in a pressure of 5, a volume of 50, and 2.1 for N, and the same R value, 5 times 50 is 250 divided by 2.1, that's 119, divide that by 0.08206, and you get about 1450 Kelvin. Now it's really close to 1451. It's 1450.7 because this answer was rounded. So I'm going to leave it as 1450. I'm going to round it to a nice whole number. So this answer is an estimate, so to speak. Now what about the temperature at point B? Notice that the pressure increases from 5 to 40 going from A to B. So 40 divided by 5 is 8. So the pressure increases by a factor of 8. At constant volume, if you increase the temperature, the pressure will increase proportionally. That means that we have to increase this value by a factor of 8. 290 times 8 is equal to 2320 Kelvin. Now going from D to C, the pressure increases by a factor of 8. So we can multiply 1450 by 8, and that will give us 11,600 Kelvin. Or we can go from B to C, where the volume increases by a factor of 5. So 2320 times 5 will also give you 11,600. So now what about part B? How can we calculate the heat transferred and paths AB, BC, CD, and DA. Well, let's start with AB. There's many different equations that we can use, but the first thing that we need to realize is this is an isochoric process. The volume is constant, so we can use this equation, NCV delta T. So N is 2.1, CV for an ideal diatomic gas is 5/2 times R, and the change in temperature going from A to B, it's final minus initial, so that's 2320 minus 290. So this is going to be about 88,600, rounded to 3 sig figs. Now, what about QBC? Here we have an isobaric process. So we can use the equation NCP delta T. Now the CP value for a diatomic gas is going to be 7/2 times R. And going from B to C, the final temperature is 11,600 minus the initial temperature of 2320. So this is going to be about 567,000. So let me take a minute and just clear away a few things. In the meantime, go ahead and calculate the other two Q values. Now let's calculate QCD. This time, let's use a different equation. We have another isochoric process, but instead of using the NCV delta T equation, let's use VCV delta P divided by R. The volume is 50 liters. CV for diatomic gas is 5/2 times R. The change in pressure is -35. And we can cancel R. And let's not forget to multiply it by 101.3. So this is going to be negative 443,000 joules. I'm rounding each answer to 3 sig figs. Now what about the last part? QDA. So going from D to A, how can we calculate it? So let's use this equation since we have an isobaric process. The pressure is constant. So let's use the equation P, CP, delta V divided by R. So the pressure is 5 atm, CP is 7/2 times R, and the change in volume, final minus initial, 10 minus 50, is -40. So we can cancel R. So as you can see, whenever you go up and to the right, Q is positive. When you go down and towards the left, Q is negative. And you can tell by the change in temperature. To increase the temperature, typically you have to put heat into the system. And to decrease the temperature from 11,000 to 1450, you have to remove heat from the system. So now let's calculate this value. So 5 times 3.5 times negative 40 times 101.3, this is about negative 70,900 joules. So now that we have the Q values for each step, let's calculate the net Q value for the cyclic process. So as we travel from position A to B, B to C, C to D, D to A, let's find the net amount of heat energy absorbed or released into the system. So we just got to add these four values. 88,600 plus 567,000 minus 443,000 minus 70,900. This is equal to positive 141,700. Now, what is the work done in the cyclic process? We know the work done is equal to the area of the shaded region. And since we have a rectangle, it's basically the length times the width. The length is basically the change in pressure. The width is the change in volume. The change in pressure is 35 if you subtract 40 minus 5. And the change in volume, 50 liters minus 10 liters. That's 40 liters multiplied by 101.3 to convert it to joules. And this will give you about 141,820. But let's round these values to approximately 142,000. It's about the same if we keep it to 3 sig figs, as we've been doing for each of these problems. Now, based on rounding errors, there's going to be some slight differences, but theoretically, these two should be equal, which they are. Now, let's think about what this means. We see that Q and W are the same. The question is why? Now, we started at position A. We went all around the rectangle, and we ended back at position A. So going from A to A, the internal energy is the same. There's no change. Therefore, delta U is equal to 0 for any cyclic process. And if delta U is equal to 0, and we know that Q is delta U plus W, therefore Q is equal to a W for any cyclic process. And that's why we can see they're the same. The area is not only equal to the work done, but also it's equal to Q because it's a cyclic process. Now let's talk about something else, but first let's get rid of a few things. What is the total amount of heat energy that went into the system? Let's say if this block represents the system. If we add these two values, we're going to get how much heat energy flowed into the system. And that's about 655,600 joules of energy went into the system. This is also known as QH. Now, how much heat energy went out of the system? That's basically these values, because they're negative. If we add them, this is going to be negative, or just simply 513,900 joules. This is also known as QL. That's the amount of heat energy lost to the environment. QH is the amount of heat energy that enters into the system. The work is the difference between these two values. 655,600 minus 513,900 is equal to approximately 142,000 if you round it. So that's how much energy that came from heat and that was transferred into mechanical work. Now let's calculate the efficiency of the system. The efficiency is basically the output work divided by the total heat energy that went into the system, that is QH, times 100%. So that's going to be 142,000 divided by the 655,600 times 100%. So the efficiency is 21.7%. So what this means is that this particular system can take 21.7% of the heat energy that is transferred to it and convert that heat energy into useful mechanical work. The other 78.3% is lost to the environment, which is a lot of energy that's lost. So these devices are not very efficient, but nevertheless, you can still use it to perform useful mechanical work. Ethane gas has a gamma ratio of 1.22. What is the molar heat capacity of ethane at constant volume and at constant pressure? So how can we find Cp and Cv given this gamma ratio? Gamma is Cp divided by Cv. It's the ratio of these two different molar heat capacities. And we know that Cp is equal to 5 over 2R. That's basically the same as 2.5R. And Cv is 3 over 2R for monatomic gas. That's 1.5R. Now, 2.5R is equal to 1.5R plus 1R. 1.5 plus 1 is 2.5. So therefore, we can say that Cp is equal to Cv plus R. So using this relationship, which is very accurate for ideal gases, we can say that gamma is equal to Cv plus R divided by Cv. So basically, we replace Cp with Cv plus R. And we could separate this into two fractions. We could divide Cv by itself and R by Cv, which means that gamma is 1 plus R divided by Cv. So let's subtract 1 from both sides. If we do that, we're going to get this. And if this is the same as gamma minus 1 over 1. If we flip both sides, this is 1 over gamma minus 1 is equal to Cv divided by R. And now if we multiply both sides by R, we can see that Cv is equal to R over gamma minus 1. So this is how you could find Cv from gamma using that equation. Now there's one more equation that we can write. So keep in mind, we said that gamma is Cp divided by Cv. So if let's move this way. If we multiply both sides by Cv, Cp is gamma times Cv, and Cv is equal to that equation. So Cp is R times gamma over gamma minus 1. So this is another useful equation. So with these two equations, we can find Cp and Cv if we're given the gamma ratio for a gas. So let's calculate Cv. That's going to be 8.3145 divided by 1.22 minus 1. 1.22 minus 1 is simply 0.22 on the bottom. So 8.3145 divided by 0.22 gives us a CV value of 37.8. So that's the first answer. That's the molar heat capacity at constant volume. Now at constant pressure, we can take R, which is 8.3145, multiply it by gamma, divided by gamma minus 1. So 8.3145 times 1.22 divided by 0.22 is 46.1. So that's the molar heat capacity at constant pressure. So that's how you can find it given the gamma ratio. Here's another problem that we could try. How much heat is required to raise the temperature of 6.5 moles of propane from 30 Celsius to 50 Celsius at a constant pressure of 2 atm? And we're given the gamma ratio. Well, to find Q at constant pressure, we can use the equation Q is equal to NCP delta T. So we got to find CP first. And we can use the equation that we got in the last problem, which is R times gamma over gamma minus 1. So that's 8.3145 times 1.127 divided by 1.127 minus 1, which on the bottom is 0.127. So 8.3145 times 1.127 divided by 0.127 is about 73.78. So using this, we can now calculate Q. So Q is going to be equal to N, the number of moles, which is 6.5, times CP, which is 73.78, times the change in temperature, final minus initial, 50 minus 30, that's 20. So 73.78 times 6.5 times 20 is equal to 9,591.4 joules. So that's the answer to the first part of the problem. Now for the second part. What is the change in the internal energy of the gas? To find the change in internal energy, we can use Q minus W, but we don't know the work, so we can also use N CV delta T, which is true for any process. So we got to find CV before we can use that equation. So let's go ahead and do that. And we know that CV is equal to R divided by gamma minus 1. So that's 8.3145 divided by 1.127 minus 1. So 8.3145 divided by 0.127 is around 65.47. So delta U is going to equal to the number of moles, 6.5, times CV times delta T, which is still 20. So 6.5 times 65.47 times 20 is equal to 8,511.1 joules. And that's it for this problem. Now here's a question for you. Let's say if you have a PV diagram with 3 isothermal graphs, which looks like this. Let's say the first one is graph A, this is B, and this is C. And there's 3 temperature values, 300 Kelvin, 400 Kelvin, and 500 Kelvin. So with this information, which graph is which one? Which one occurs at which temperature? Let's say we have pressure on the y-axis, volume on the x-axis. If you ever see a question like this, you need to know that the temperature increases as you go up in this general direction. Whenever you go to the right, the temperature increases because the volume increases at constant pressure. According to Charles' law, when you increase the temperature, the volume goes up. And when you go up, the increase in temperature causes an increase in pressure at constant volume. At constant volume, when you increase the temperature, the pressure goes up. So therefore, C is at the highest temperature, that is at 500 Kelvin. A is at the lowest temperature of 300 Kelvin, which means B is in the middle at 400 Kelvin. So anytime you go in this general direction, the temperature increases. Make sure you understand that for PV diagrams. Now let's spend some time talking about the graph of an adiabatic expansion. And let's see how it differs from an isothermal expansion. So let's say this is an isothermal expansion from A to B. Keep in mind, for isothermal graphs, or any isothermal process, delta T is equal to 0. The change in temperature is 0, so the temperature remains constant. Now for an adiabatic expansion, it looks very similar, but notice that the curve is lower. So A to C is an adiabatic expansion. And for that, Q is equal to 0. No heat enters or leaves the system. But notice that the temperature drops. So this is, let's call this AD adiabatic expansion. This is the isothermal graph. So for adiabatic expansion, when the volume increases, the pressure decreases, but it happens in such a way that the temperature drops. For an isothermal graph, when the volume goes up, the pressure goes down. But because the temperature is constant, for an isothermal graph, you can use the equation P1V1 is equal to P2V2. Now, because the temperature changes in the adiabatic expansion, because it cools down, you need to use a variant of this equation. The equation that you need to use is P1V1 raised to the gamma power is equal to P2V2 raised to the gamma power. So as you can see, it looks like that equation, but slightly different. And there's also another equation that you need to know. It's T1V1 raised to the gamma minus 1, which is equal to T2V2 raised to the gamma minus 1. We can talk about how to derive this equation later. But let's work on a problem using those equations. A car engine takes in air at 25 degrees Celsius and 1 atm and compresses it adiabatically to 0.1 times the original volume. The air has a gamma ratio of 1.4. What is the final temperature and pressure? So we know that the temperature decreases during adiabatic expansion, but during adiabatic compression it increases. And if you decrease the volume, the pressure will go up, and it turns out the temperature will go up as well. So let's work out this problem. Let's begin by using the equation P1V1 raised to the gamma value is equal to P2V2 raised to gamma. Now let's make a list of the information that we have. T1 is 25 Celsius, and if you add 273 to it, that's going to equal 298 Kelvin. Now we don't know what T2 is equal to. We know that P1 is 1 atm, and we don't have the value for P2. We need to find that as well. We don't know what V1 or V2 is equal to. However, we do know the ratio. It's 0.1. So let's say if V1 is 1 liter, that means V2 is going to be 0.1 times that, 0.1 liters. It really doesn't matter the actual values of V1 and V2. The relative values is what matters. If V1 was 10 liters, V2 would be 10 times 0.1, which is 1. So regardless if you use 1 and 0.1 or 10 and 1, the answer will still be the same. Now, if you've taken general chemistry, perhaps you've seen the combined gas law equation. Now, if we had T2 or P2, we could find the missing value, but here we have two missing values. So therefore, the combined gas law won't help us. We need to use this equation to find P2, and then the other equation to find T2. So let's begin. P1 is 1, V1 is 1 raised to the gamma, which is at 1.4. We're looking for P2. V2 is 0.1 raised to the 1.4. So to solve for P2, it's going to be 1 raised to the 1.4, which is simply 1, divided by 0.1 raised to the 1.4. So P2 is about 25.1 atm. Now let's use the other equation. T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. So T1 is 298 Kelvin, V1 is 1, gamma minus 1, that's 1.4 minus 1, which is 0.4. We're looking for T2, and V2 is 0.1 raised to the 0.4. So T2 is going to be 298 times 1 raised to anything is 1, so 1 to the 0.4 is 1. So it's 298 divided by 0.1 raised to the 0.4. And you should get 748.5 Kelvin. If you subtract that by 273, that's 475.5 Celsius. Now let's talk about this. But first let's make some space. Now the volume changed from 1 liter to 0.1 liters. So the volume decreased by a factor of 10. When the volume goes down, the pressure goes up. But notice that all we did was we decreased the volume by a factor of 10, and the pressure increased more than a factor of 10. How did that happen? Well, it has to do with the change in temperature. By decreasing the volume by a factor of 10, the pressure actually goes up by a factor of 10. They're proportional according to Boyle's law. But let's look at the temperature. The temperature changed from 298 Kelvin to 748.5 Kelvin. When you increase the temperature, you also increase the pressure. If we divide 748.5 by 298, it tells us that the temperature went up by 2.51. So therefore the pressure should go up by 2.51. If you multiply these two values, you can see the pressure went up by a combined value of 25.1. So it increased by a factor of 10 due to the decrease in volume, and it increased by a factor of 2.51 due to the increase in temperature. So as you can see, the pressure and the temperature greatly increased in this situation, which means adiabatic compression is very useful for engines, if you think about it. As the gas compresses adiabatically, the increase in pressure and the increase in temperature greatly accelerates the reaction between the air and the fuel. At high pressures, gas molecules collide more frequently, which increases the rate of the reaction. Also, if you increase the temperature, they collide not only more frequently, but also with more energy, making the reaction more spontaneous. And as a result, when you compress the air-fuel mixture adiabatically, you really don't need a spark plug. The high temperature and pressure could ignite the mixture spontaneously, which is very useful for engines. Now let's talk about how to derive those equations. For an adiabatic process, we know that there's no exchange of heat. The heat flow into or out of the system is 0, so Q is 0. And according to the first law of thermodynamics, the change in internal energy is Q minus W. So if Q is 0, that means delta U is equal to negative W. And we know that delta U for any process is NCV times delta T. And the work is typically pressure times the change in volume. And according to the ideal gas law, PV is equal to nRT. So if we solve for P, it's nRT divided by V. So let's replace P with this expression. So now we have the expression NCV delta T is equal to negative nRT over V times delta V. So we can cancel the number of moles, which is N. And so we're left with CV delta T is equal to negative RT delta V divided by V. So now what we're going to do is divide both sides by T and CV. So I'm going to divide the left side by CV and T and the right side by CV and T. So on the left side, T is going to cancel, and on the right side, CV will cancel. So I now have the expression delta T divided by T is equal to negative RV over CV delta V divided by V. Now, if you recall, CV is equal to R divided by gamma minus 1. If we multiply both sides by gamma minus 1, or even if we cross multiply, CV times gamma minus 1 is equal to 1 times R, which is R. So if we divide both sides by CV, gamma minus 1 is equal to R over CV. So now we can replace R over CV with gamma minus 1. So we have delta T divided by T is equal to negative gamma minus 1 delta V over V. Now let's take this expression, let's move it to this side. So it's delta T divided by T is equal to positive, well not equal to, but plus gamma minus 1 times delta V over V, and this is equal to 0. Now delta T, if the change is very small, we can say it's approximately equal to dt, and delta V, given a small change in V, we could say that's equal to dV. So I'm going to rewrite the expression as 1 over T times dt plus gamma minus 1 over V times dV, and this is equal to 0. So now we're going to find the antiderivative of both sides of the equation. So let's integrate 1 over T, 1 over V, and 0. Gamma minus 1 is a constant, so we can move it in front of the integral. Now, if you recall, we said the antiderivative of 1 over x is ln x. So the antiderivative of 1 over t is ln t. And the antiderivative of 1 over v is simply ln v times the constant in front of it, which is gamma minus 1. The antiderivative of 0 is equal to a constant. Now, a property of natural logs allows us to take the constant in the front and move it to the exponent position. So 2 ln a is equivalent to ln a squared. So using that property of natural logs, we can take the value gamma minus 1 and move it onto the exponent of v. So ln t plus ln v raised to the gamma minus 1 is equal to a constant. Another property of logs that we can employ is this property. ln a plus ln b is equivalent to ln a times b. So we can take two natural logs and compress it into a single natural log. So ln t times v raised to the gamma minus 1 is equal to a constant. So ln T1 V1 gamma minus 1 is equal to a constant, which is equal to ln T2 at a different temperature and V2 at a different volume, but raised to the gamma minus 1. So if these two are equal to the same constant, they must be equal to each other. So we can say that T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Now at this point, let's go back to the ideal gas law equation. PV is equal to nRT. This time we're going to solve for a T. PV divided by nR is equal to T if you divide both sides by the nR value. If you do that, these will cancel, and you get this expression. So let's replace T with PV over nR. So T1 is P1 V1 divided by nR. R is constant, and we're not going to change the moles of gas, so N will be constant. So T2 is going to equal P2 V2 over nR times V2 gamma minus 1. So nR is the same, we can cancel these two. Now according to the rules of algebra, if you multiply, let's say, two common variables, you can add the exponents. So x squared times x cubed is x to the fifth. 2 plus 3 is 5. Therefore, if we multiply v1 raised to the first power with v1 raised to the gamma minus 1, we can add 1 plus gamma minus 1, which is equal to gamma. So v1 times v1 gamma minus 1 is just v1 raised to the gamma. So these two combined will simply become v1 raised to the gamma power. And the same is true for the other side. It's going to be v2 raised to the gamma. So that's how we can get this equation. So now what we're going to do is go over all of the equations that we went in this video. We're just going to do a final summary, and that's going to be it for this video. Now the first and most important equation that you need to know is the first law of thermodynamics, which is basically the change in internal energy is equal to Q minus W. Anytime heat is absorbed by the system, Q is positive. And when heat is released, Q is negative. When work is done by the system, work is positive. And when work is done on the system, work is negative. So let me just write that. This is by the system, and this is on the system. Now the system performs work whenever the gas expands. Now to do work on a system, ideally on a gas, you need to compress it. So compressing a gas, work is always negative for that process. Now delta U is always dependent on temperature. Delta U is equal to N CV delta T for any process. So if the change in temperature is 0, delta U is 0. If the temperature increases, then the internal energy will increase as well. So this is the next equation that you need. Now keep in mind, for monoatomic gases like helium, neon, argon, CV is approximately equal to 3 over 2 times R, and CP is 5 over 2 times R. Now R has two values. For the most part, R is usually 8.3145 joules per mole per Kelvin. But if you're dealing with gases where P is in ATM and V is in liters, sometimes you may use this equation. Typically, you may need to use this R value for the ideal gas law equation. PV is equal to nRT. But going back to gases, if we have a diatomic gas like N2 or O2 or even H2, you can approximate CV using this equation, 5 over 2 times R. And Cp is 7 over 2 times R. And if you have a gas with 3 atoms like CO2, SO2, it's better to look up the Cp and Cv values. But if you don't have it, if you can't look it up, the best thing you could do is estimate the answer. So Cv is going to be equal to 7 over 2R, and Cp is approximately equal to 9 over 2R. So this is approximately equal to. There will be some variations. Now the first process that we need to talk about is an isochoric process. In a PV diagram, it looks like this. It's basically a straight line going up or down. For an isochoric process, the change in volume is 0. So therefore, the work performed is 0. Since there's no area, there's no shaded region. Because work is equal to 0, Q is equal to W. I mean, not W, but delta U. So this equation still applies. Delta U is Q minus W. And since W is 0, delta U equals Q. So you can use this equation to find delta U. NCV delta T. This will always work. And Q is also equal to NCV delta T because the volume is constant. So those equations are the same since they equal each other. Now there's more. For an isochoric process where the change in volume is constant, is equal to 0, you can also use this equation. Q is equal to V CV delta P divided by R. So this equation applies. And also, since the volume is constant, when the temperature goes up, the pressure will go up proportionally. So you can also use this equation. P1 divided by T1 is equal to P2 divided by T2 during an isochoric process. So that's it for this process. Now let's move on to the next one. Now, let's talk about the isobaric process. This is when the pressure is constant. So delta P is equal to 0. And the PV diagram looks like this. You can travel to the right or to the left. Now keep in mind, whenever you travel towards the right, the work performed by the gas is positive. And if you travel towards the left, the work performed by the gas is negative. And remember, the work performed is equal to the area of the shaded region. So for an isobaric process, the work is equal to P delta V. This is the equation that you want to use. Now you can also find the work in terms of temperature. It's equal to nR times delta T. Since PV is equal to nRT, P delta V is equal to nR delta T. So that's another way you could find the work during an isobaric process. Now to calculate Q during an isobaric process, you can use the equation N Cp delta T. You can also use the equation P Cp delta V, since the volume changes, divided by R. And delta U is still Q minus W. This equation applies, and it's also equal to NCV delta T. Now for an isobaric process, since the pressure is constant, when you increase the temperature, the volume will increase. And according to Charles' law, you can use this equation. V1 divided by T1 is equal to V2 divided by T2. Now let's say if you have a cyclic process, which looks like this. As we mentioned before, the work performed by the gas is equal to the area of the shaded region. And since we have a shape of a rectangle, the area is basically the length times the width. The length is the change in pressure, the width is the change in volume. So in this instance, the work is equal to the change in pressure times the change in volume. So that's a combination of an isobaric and an isochoric process. Now, if you have a PV diagram that looks like this, let's say if you start at an initial pressure and it increases to a final pressure, and also the volume changes from an initial value to a final value, the work performed is still the area of the shaded region. But a simple way to calculate this area is to use this equation. It's to use an average pressure. To find the average pressure, you still use the equation P delta V, but to find the average pressure, you simply add up the initial and the final pressure and divide it by 2. So the work performed is 1/2 the sum of the two pressures times the change in volume. That's if the pressure changes at a constant rate. It can increase or decrease. As long as that line is a straight line, you can use this equation. If you want to, you can calculate the area by turning this into a rectangle and a triangle. So if you find the area of the rectangle and the triangle, you can also calculate the area, which is equal to the work. The area of a rectangle is length times width. The area of a triangle, 1/2 base times height. Now there's one more thing we need to talk about. So let's say if we have a cyclic process. So you know how to find the work, which is the area of the shaded region. But you need to know if it's positive or negative. So if the process is moving in the clockwise direction, the work performed is positive. But if you have a cyclic process moving in the counterclockwise direction, then the work performed is negative. So keep that in mind. And also, the net heat flow during a cyclic process is equal to W, because as you start from position A, going to B to C to D and back to A, going from A to A, the change in internal energy is 0. And since delta U is Q minus W, if delta U is equal to 0, that means Q has to equal W. So for any cyclic process, the total heat flow, or the net heat flow, is basically W. The net heat flow is the amount of heat that enters the system minus the heat that leaves the system. QH represents the energy that enters the system. That's the total heat absorbed by the system. QL represents the energy that is released by the system. And the difference between those two is equal to W. The efficiency is basically the work performed divided by the total heat that entered the system. These two values are different. This is usually larger. So the efficiency is W minus QH, but also times 100%. The third process that we need to review is the isothermal process. Iso means the same. So isothermal, the temperature is going to be the same. So the change in temperature is 0. Now the isothermal graph looks like this in the PV diagram. To calculate the work performed in an isothermal situation, you can use this equation. It's equal to nRT times ln V final divided by V initial. You can also use this equation, nRT ln P final divided by P initial. Now, because the change in temperature is 0, that means delta U is equal to 0. Keep in mind, delta U is NCV delta T. So if this part is equal to 0, the whole thing is equal to 0. Now, if delta U is equal to 0, and delta U is Q minus W, that means Q minus W is equal to 0, which means Q is equal to W for an isothermal process. So you can also find Q using any one of these equations since it is equal to W. Now, since the temperature is constant for an isothermal process, that means that as you increase the volume at constant temperature, the pressure decreases proportionally. So you can also use this equation. P1 V1 is equal to P2 V2. That is Boyle's law. So that's it for an isothermal process. Now let's move on to an adiabatic process. In this process, the insulation is either very, very good, or the process happens so quickly that heat doesn't have enough time to enter into or out of the system. So for an adiabatic process, Q is approximately equal to 0. And if that's the case, that means that delta U is equal to negative W, since Q is 0. So we know we could find delta U using this equation, NCV delta T, for any process. That means that you can also find the work using the equation negative NCV delta T. Now keep in mind, you can find CV by using this equation. It's equal to R over gamma minus 1, where R is 8.3145. And CP is equal to R times gamma over gamma minus 1. And gamma is the ratio between CP and CV. And then you also have these equations. P1 V1 raised to the gamma is equal to P2 V2 raised to the gamma. And also T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Now you can also find work using some other equations. So starting with this equation, negative NCV delta T, it might be useful to write this equation in terms of pressure and volume. So using the equation PV is equal to nRT, the change in PV is equal to nR times the change in delta T. So the change in PV divided by nR is equal to delta T. So we have NCV times delta PV over nR. So N cancels. So here's another equation that you might find useful. The work is equal to negative CV divided by R times P final V final minus P initial times V initial. So that's another equation that might be useful if you need to calculate the work performed in an adiabatic process. And if you don't have the temperature, but if you have the pressure and the volume, you can use that as well. You can also use this equation. W is equal to negative 1 over gamma minus 1 P final V final minus P initial V initial. You can get that equation using the fact that CV is R over gamma minus 1. If you cross multiply, CV times gamma minus 1 is equal to R. And if you divide both sides by, let's say, CV, gamma minus 1 is R over CV. Therefore, 1 over gamma minus 1 is CV over R. So you replace this with 1 over gamma minus 1, and that's how you get the other equation. So basically, that's all the equations that you need for this particular topic. So that is it for this video. Thanks for watching, and have a great day.